Welcome to Introduction to Composites. Today is the third day of this ongoing week, and today what we will discuss is stress strain relationship for an orthotropic lamina. So, that is the focus of our discussion. So, essentially what we will like to understand is that if I apply some stresses on an orthotropic lamina, how can we predict the strains in it and vice versa. So, analysis of orthotropic lamina. And we have discussed what is an orthotropic lamina, but for purposes of completeness we will just quickly recap what orthotropy implies. So, first we will consider an isotropic material. Isotropic material, and for such a material and this is an isotropic material, and if I pull it, so I just pull it, I only apply extensional force on it, then it becomes longer and also it becomes thinner or slimmer. Okay. So, this is the response. So, extensional stress, it causes only extensional strain. So, the thing becomes longer, that is an extensional strain, and it becomes slimmer, that is also an extensional strain, but in the negative direction. So, this is how isotropic materials behave. And if I have the same material and I subject it to a pure shear stress, if I apply and I subject it to pure shear stress, then I get pure shear strain. So, the thickness and the length of the object they do not change. So, shear stress it generates only shear strain. This is the behavior, observed behavior of isotropic materials. In contrast, if I have an isotropic material, then extensional stress it generates extensional strain and it also generates shear strains. It also generates shear strain. So, to visualize it, if I have a rectangular block and I subject it to sigma x, it will not only become thinner and longer, but it will also distort in shape. Okay. It will also distort in shape. So, this angle will also change. So, external stress causes not only extensional strain, but also shear strain. And if I apply a pure shear stress, what does it do? It also generates extensional strain plus shear strain. It generates extensional strain plus shear strain. So, these are anisotropic materials. Then we have orthotropic materials. This is the third case. Orthotropic materials. And when we say orthotropic materials, what does it mean? We had discussed this earlier, that they have 3 different material axes. So, what are those material axes? L, T and T prime. Okay. And in general, so we will consider 2 special cases, 2 situations here. Situation 1, in situation 1, load is not aligned with, it is not aligned with material axis. And in this case, the behavior is similar to anisotropic materials. Okay. Similar to anisotropic materials. So, what do I mean when load is not aligned with material axis? So, let us say this is the material and I am pulling it in x direction. So, this is my x direction, sigma x, and the material axis is not aligned. So, the material axis could be at some angle. So, maybe this is the L direction. So, fibers are running at an angle theta to the thing. So, in that case, the behavior is similar to anisotropic materials. Okay. So, this is situation 1. So, in this case, the response of the material is that of a orthotropic material, but this is general orthotropy. So, it is generally orthotropic. Okay. And then we have situation 2, where load and material axis are aligned. So, how does it look like? You have the material, let us say this is sigma x, and the fibers, either they are in the L direction or they are in the T direction. So, in this case they are in the L direction. Okay. So, this is my L direction and this is my T direction. So, when load and material axes are aligned, then behavior is similar, it is similar to isotropic material. So, this is the case of special orthotropy. So, in this case, if you apply an extensional stress, it will only generate extensional strains, it will not generate shear strains. And if you apply a pure shear stress such that the shear stress directions are aligned with material axis, then it will generate only shear strains, it will not generate extensional strains. So, these are the different situations, these are different situations. So, we have the case of isotropy, we have the case of anisotropy, and then we have the case of orthotropy, and in orthotropy we can have two kind of situations. General orthotropy, where the behavior of material is similar to that of anisotropic materials, and special orthotropy, where the material behaves as an isotropic material. So, here now what we will do is we will discuss first special orthotropy and then we will go to general orthotropy. So, we will start with special orthotropy. So, this is my material, and let us say this is the direction of the fibers. So, this is my L direction, this is the T direction, and the direction normal to the plane of this board is T prime direction. So, this is T prime direction normal to the plane of this screen which you are watching. Now, we had mentioned earlier in one of the classes, and this later we will actually prove it, is that a especially orthotropic material, so it has 4 independent elastic constants. So, what are those? Those are EL, ET, and we have learned how to calculate these if we know the material properties, GLT and mu LT, and then mu TL can be calculated in terms of EL, ET and mu LT. So, these are the 4 independent elastic constants. This one mu LT is called major Poisson's ratio. We have again discussed this earlier. And this one is known as minor. It is a minor Poisson's ratio. Now, let us look at the stress strain behavior of this material. And we will look at 4 different cases. Case 1. So, if sigma L is not 0, and so this kind of a material we can apply 3 different loads on it, 3 different types of stresses: sigma L, sigma T and tau LT. Those are the 3 things. So, if sigma L is not 0, but sigma T equals tau LT equals 0, then what will happen? This system will generate strains. In that case, epsilon L is what? Sigma L divided by EL. This is how we have defined EL. And because the thing becomes a little longer, it will also become slimmer because of the Poisson's effect. So, the transverse strain epsilon T will be what? It will be minus mu LT times epsilon L. Why is it mu LT? The first subscript tells us the direction of the loading. Direction of loading is L direction. This is the direction of the loading, L direction, and the second subscript tells us the strain direction. So, strain is happening in the transverse direction because it is shrinking. So, epsilon T equals negative of mu LT times epsilon L. Okay. And what is epsilon L? Epsilon L is nothing but sigma L over EL. So, this is what I will write. Now, this is a especially orthotropic material, the load direction and the direction of the fiber is aligned. So, in this case I am applying only extensional stress in it, so there will be no shear strain. So, gamma LT equals 0, gamma LT is equal to 0. So, this is case 1. Next, look at case 2. In case 2, we apply a pure transverse stress, only a transverse stress. So, in this case sigma L is equal to tau LT is equal to 0, but sigma T is not equal to 0. So, when I apply a pure transverse stress, what will happen? It will have a transverse strain. So, epsilon T equals sigma T by ET, and as this thing becomes longer in the transverse direction, it will also become narrower in the longitudinal direction because of Poisson's effect. So, epsilon L is equal to minus nu TL times epsilon T, but epsilon T is what? Sigma T over ET. So, I will just erase this and replace it by this. So, it is sigma T over ET, and once again, so here what is, how are we loading it? My fibers are like this and I am loading it in transverse direction. Okay. So, here also the loading is aligned with the axis, here the load is aligned with the transverse axis, and so I am just applying a pure extensional strain, and because it is the case of special orthotropy, there will not be any shear strain gamma LT. So, gamma LT will be 0. The third case is that of a pure shear stress. So, here sigma L equals sigma T is equal to 0, only shear stress is present, only shear stress is present. So, and so this is my L axis and I am applying a shear stress. So, please note this convention of shear stress is positive. If I applied shear stress in the other direction, then it would be negative shear stress. So, this is a positive shear stress, this is our convention, and in this case gamma LT equals tau LT by shear modulus of the material, and the extensional strains in transverse and longitudinal directions, they are both 0 because of special orthotropy. So, in the first case I applied only an extensional stress in the length direction, longitudinal direction, here pure extensional stress in the transverse direction, and here pure shear stress. And now we will discuss a fourth case. Case 4, and what is case 4? All the stresses sigma L, sigma T and tau LT are present. So, sigma L is not equal to 0, sigma T is not equal to 0 and tau LT is not equal to 0. So, how does the loading look like? So, this is my orientation of fibers. I am applying a stress in the in the longitudinal direction. I am also applying a transverse load or stress, and I am also applying a shear stress. And I am also applying a shear stress. So, this is what I am applying. So, in this case I am interested in finding out the strains. So, I want to find out epsilon L, I want to find out epsilon T, and I want to find out gamma LT. Now, how do we do this? We already know that if there is pure stress in L direction, then these are the strains. If there is pure only stress in the transverse direction, then these are the strains, and if there is a pure shear stress, then these are the strains. So, and in the fourth case all the three stresses are present. So, we just use the principle of superposition and just add up all the values and we get the overall strains. So, overall strain in the longitudinal direction is strain in L direction due to sigma L. So, what is that? Sigma L divided by EL plus strain in L direction due to sigma T, and that will be the Poisson's component. So, it is mu TL sigma T over ET, and the shear stress will not create any extensional strain. Similarly, epsilon T is equal to sigma T over ET. This is the component just due to sigma T plus the effect of Poisson plus the Poisson effect when you are applying sigma L, and that is minus mu LT sigma L over ET, or sigma L over EL, and this is equal to tau LT over GLT. Okay. So, these are the overall strains in the whole system. So, we can write this also in a matrix form: epsilon L, epsilon T, gamma LT equals so on my this side I will have vectors sigma L, sigma T, tau LT, and here I have 1 over EL minus nu TL by ET 0 minus nu LT by EL 1 over ET 0 0 0 1 over GLT. So, this is the situation. Okay. So, what we have shown till so far is now with these relations. So, this is the matrix form or this is the general relation, a conventional form. If we have especially orthotropic lamina which is subjected to stresses in longitudinal, transverse and shear directions, then we can predict its strains using these equations. So, this concludes our discussion for today. Tomorrow we will continue this discussion and we will also start exploring the relationships for generally orthotropic lamina. So, with that I close my lecture for today and I look forward to seeing you tomorrow. Thank you.